In this example, we're going to see how we can use the OpenOffice nonlinear solver to help us fit a nonlinear regression model. So I have opened up OpenOffice, the calc application in OpenOffice, and I have some raw data, as you can see here, my x and my y variables, my independent and dependent variables, ranging from -10 to +10 on my x variable, and from about, say, 100 to 300 for my y variable. So I have this data graphed in a scatter plot, and we would like to fit a function that basically minimizes the least squares between all these data points and our function. I'll explain that here in just a moment. So before we use OpenOffice, let's go in and use some statistical software and see what function this software would fit for us. So the software that I'm using is JMP. It's a well-known statistical software, and I'm going to fit a nonlinear function to this data that I have in JMP. And the function that I'm going to fit, let's take a look at this function. It is beta naught plus beta 1 divided by 1 plus e raised to the beta 2 plus beta 3 times x. So this is the function that we're going to be fitting. This is a standard S-shaped or sigmoidal function. And I have 4 parameters, beta 1 through beta 3. So I'm going to initialize these values, say, at 1, and solve. And the values that it has given me, as we can see, beta naught 283.53, beta 1 -165, beta 2 -1.77, and beta 3 0.544. So let's see what OpenOffice does for us. So this is the raw data that I have, these 2 columns. I have created a column with the function as a function of these 4 cells, F1 through F4. So if we examine this function, we can see that this is the function that we used in JMP. And we have to make sure that we lock in the values of beta 1 through beta 3, or F1 through F4. So we use these $ to lock in these values. And then we simply drag this to the end, or we can double click it. And what it will do is it will create values based on what our x values are. Okay. And I also have these graphed. So the red line is the function. So if I were to change the beta 1 value to, say, 100, we can see how this line moves up. So we can see that the beta 1 value simply translates our function up. Okay. So what I'm going to do, because I have this graphed, anytime I change these values, it will try to update this graph, so it's going to slow down the nonlinear solver. So I'm going to go to a tab where I don't have this graph displayed. I have created a column here which is the sum of squared difference between our actual values and our predicted values. So it's simply B2 minus C2, the quantity squared, or this value minus this value, the quantity squared. And then this cell here is simply the sum of all of my squares, or the different squares. So it's just the sum of squares. So I've simply summed up this column. So as I change these values, you can see how the sum of squares will change. And if you remember from your statistics class, when you fit a nonlinear model or any regression model, most of the time you're trying to minimize the sum of squares. So what we're going to do is go to OpenOffice Solver, and we are going to create a nonlinear model that tries to minimize this value. So for my target cell, I want to try to minimize this cell. Minimize by changing these 4 parameters. And I'm also going to plug in some constraints for these parameters. I don't know what they are, but if I plug in some constraints, it will help the solver identify what these values are quicker. So I'm going to say, well, let's let these 4 values be they're probably going to be less than, say, 500. That's a really large number for these parameters. And these 4 values are probably also going to be greater than, say, -500. And if I look at my raw data, I can see that because B1 simply translates this function, that B1 is probably also going to be greater than 0. So if I plug in, say, a value of 100, we can see how this line moves up. So it's simply just it's used to translate the function. So I'm going to say, let's let B1 also be greater than 0, just to put in some value. And then for the most part, I really don't have any insights of what these other values should be. I'm not familiar enough with the function. I do know the function that I'm trying to fit, like I said, is beta naught plus beta 1 divided by 1 plus e raised to the beta 2 plus beta 3x. And this translates into a sigmoidal function that looks like this. And like I said, I know what impact beta naught has on my function. Beta naught is what translates this function upwards. So like I said, I do know that it is greater than, beta naught has to be greater than 0. But I really don't know what these values are. So I'm just going to pick relatively large values, say between 500 and negative 500. And I'm simply going to solve this now. So this uses a nonlinear algorithm, uses a evolutionary solver similar to a genetic algorithm. There's also a couple other options in an OpenOffice solver that we can use. So it's a little bit slower than JMP. The reason why this is the case is because OpenOffice solver is just a general nonlinear solver, whereas JMP is specifically designed to solve regression models. But nonetheless, hopefully we'll get an answer here shortly. We can see that the current solution, it is decreasing. It started at around 6.8 million for the total sum of squares. We're already down to 127,000. If we go in and look at our JMP model, we can see that the sum of squares that JMP solved for is approximately 42,934. So hopefully it will reduce this value down to around 43,000, and at that point we will know that we have reached an optimal solution. So let's give it just a minute. We can see that these values have changed, and in just a moment we will plug these values into our previous sheet and see how well the curve fits. So it looks like it's really starting to decrease at this point, and hopefully in another few seconds we will have an optimal solution. And if we're lucky, we'll get the exact same answer that JMP gave to us. So we're already down to 44,000. We need to get to 43,000, 42,000. And remember, we can use OpenOffice to solve any nonlinear function. So you can have as many independent variables and as many parameters as you need. The closer your estimates are to begin with, the more quickly the software will converge. So we're almost there, it seems. And when we see this progress bar starting to increase, stagnation has occurred, which means we're not seeing any improvement on our solution, and we know that we have reached an optimal solution at that point. So we're already down to 42,934.05. We needed to get to 0.04, so hopefully it will reach that value here in just a moment, and then we can compare the two solutions to one another. So let's take a look at what the parameters are for JMP. We saw stagnation starting to occur there for a moment, and it looks like that it is homing in on that optimal solution. And we can see that this is the solution that OpenOffice gave us, and the solution that JMP has given us is hopefully very similar. And when we look at these values, 283.53, negative 165, negative 1.77, and 0.0544. So we can see that OpenOffice has given us the exact same parameters as GMP. So this is an example of how we can use the nonlinear sovereign OpenOffice to help us create nonlinear regression models for any data set.